Welcome back. We can now use this valuable tool, the DFT, and its fast implementations to bring signals and the operations of LSI systems in the discrete frequency domain. This is really one of the main practical objectives, performing the filtering of an image in the discrete frequency domain with the use of FFTs. We saw when we talked about the Fourier transform that convolution in the spatial domain results in multiplication in the frequency domain. It seems that this should be done, but there is a small glitch, since the multiplication of the DFTs of two signals results in their circular and not their linear convolution in the spatial domain. We therefore explain in this segment how the 2D circular and linear convolutions are related, and most importantly, what are the steps that we need to take so that the results of the linear and circular convolutions of 2D signals are identical. Often I use the term signal instead of image or 2D signal to indicate that all these results we are obtaining here are extensions of 1D processing, and similarly these results can be extended in a straightforward way to dimensions higher than 2. Visualizing, however, dimensions higher than 2 in the spatio-temporal or frequency domains, it's not always a straightforward task. So let's proceed with the material of this segment. Now that we have a computable transform, the DFT, to take us efficiently through an FFT to the frequency domain, would like to use this tool to implement filtering in the frequency domain. So let's see what are the steps to accomplish this. So we start with an LSI system shown here. H, N1, and 2 is the impulse response of the system. X is the input. The output I denoted by Y of L. And we know by now that Y of L, N1, and 2 is equal to the convolution, the two-dimensional linear convolution of X with H. I now find the DFT of the impulse response, that's the frequency response. I do the same for the input. I find the DFT of the input. And I form the output of this system by multiplying the corresponding DFT. So YK1, K2, the DFT of the output equals the DFT of the input times the DFT of the impulse response of the system. A side note here is that in order to be able to perform this multiplication, I have to have all the DFTs being of the same size. So otherwise the multiplication does not really make sense. So if the support of X and H is different, I'll have to pad them with zeros to bring them to an appropriate size. I want to bring now this equation back to the spatial domain. I would expect that the quantities I get by coming back to the spatial domain should be related, and actually our intuition tells us that the inverse DFT of YK1, K2 should be the convolution of the inverse DFT of XK1, K2 with the inverse DFT of HK1, K2. We are partially correct in the sense that what we obtain is not the linear convolution or the convolution, but instead the circular convolution of X with H. One way to think of the circular convolution is to follow the steps of the linear convolution, but now all the shifts and reflections are circular and not linear. Another way to think of the circular convolution, maybe a more useful way, is through the linear convolution as shown by this expression. So according to this, I first find the linear convolution Y of L up here of X with H, and then I periodically extend it with periods N1 and N2. R1, R2 range from minus infinity to infinity. And then after I do that, I keep just the base period. So N1 is from 0 to N1 minus 1, and N2 from 0 to N2 minus 1. It should be noted here that in order to perform circular convolution, the two signals should have the same support, and the result of the circular convolution gives me an image of the same support with the two images I'm circularly convolving. So what we've seen here is that I can utilize the efficiency of the DFT to perform filtering in the frequency domain. However, what I obtain by multiplying the corresponding DFTs in the frequency domain is the circular convolution of the two signals, the input with the impulse response. LSI systems perform linear convolution. So the key question that arises is under what conditions should the result of the linear and circular convolutions be the same? We will look into this into some detail next, although one might already have the answer. As long as there is no aliasing in performing this periodic extension, the two results, the result of the circular and linear convolution, will be the same. Let me refresh your memory here, since this is something we covered at an earlier point. If I'm convolving two signals, let's say this is my X N1 and 2 signal, this is my H N1 and 2 signal, and I'll call the result of the convolution Y of L N1 and 2. Then if the support of the first signal is as shown here, this is N1 by N2, while the support of the second one is M1 by M2, then the support of the result of their convolution is going to be, as shown here, L1, which is equal to N1 plus M1 minus 1 by L2, which is equal to N2 plus M2 minus 1. This is a rather straightforward result to show just by following the steps of the convolution. So clearly, the result of the convolution, the output signal, has greater support than any of the individual signals I'm convolving. Now, if I want to perform linear convolution through the use of a DFT, I should utilize DFTs of size L1 by L2. So I should take the input signal and increase its size to L1 by L2 by padding it with zeros. I should do the same for the second signal I'm convolving with. So this is L2, this is L1, and here I pad it with zeros. I take the DFTs, I multiply them in the discrete frequency domain, and I take the inverse DFT, and I come back to the spatial domain. And as I mentioned in the earlier slide, the result then is the circular convolution, which is formed by the periodic extension of the linear convolution shown here. But since the periodic extension is going to be with respect to L1, L2, we clearly see here that there's not going to be any overlap between the replicas of this signal YL, and therefore the result of the circular and linear convolutions is going to be identical. We show here the periodic extension of the result of the linear convolution with periods L1, L2, as explained in the previous slide. So in this particular case, there is no aliasing. L1, L2 are chosen appropriately. If instead I choose an L1 prime, which is less than L1, and an L2 prime, which is less than L2, in performing the periodic extension, and L1, L2, L1 prime, L2 prime, by the way, are the sizes of the DFTs, then clearly aliasing is going to take place. So the resulting image, which has size L2 prime, L1 prime, is going to have the so many first rows and columns aliased, and the number of the aliased rows here, this is L1 minus L1 prime, and the number of the columns that are aliased is L2 minus L2 prime. The rest of the image, of course, the one shown here, the result of the circular and linear convolution are identical. Let's recap what we've learned so far, and I also want to make an additional point. So we're given this 8 by 8 image, and we want to convolve it with a system that has this 3x3 impulse response. First of all, we know that the result of the convolution is going to be a signal that is going to have 8 plus 3 minus 1 equals 10 in the n1 direction and 10 in the n2 direction dimension. So it's going to be a 10 by 10 image. So the steps I have to follow are the following. I'll take the original image and turn it from an 8 by 8 image to a 10 by 10 image. So I'm going to pad it appropriately with zeros as shown here. Now, as far as the impulse response of the filter goes, we see here that it is centered at 0. When I talk about DFTs, the range of values are from 0 to n1 minus 1, 0 to n2 minus 1. So I cannot accommodate the negative n1 and 2 values of this signal. So in order to handle that, I will periodically extend this 3 by 3 signal with period 10 in both dimensions. And then I'm going to pull out the base period from 0 to 9 in n1 and 0 to 9 in n2. So what's in this red dotted rectangle is a 10 by 10 image. I will pad it with zeros. So now I have two 10 by 10 images in the spatial domain. I'll take their corresponding DFTs. I'll bring them to the frequency domain, 10 by 10 DFTs. I'll multiply them, take the result of the multiplication, and bring it back to the spatial domain through an inverse DFT, and that will give me the linear convolution of the two signals I started with. One of the advantages of frequency domain filtering, in addition to possibly fast implementation, is that I can process each frequency individually. So one can selectively allow certain frequencies of the input signal go through the filter unchanged, or with some gain, or with some loss, or some of them will be completely rejected. So as a simple but hopefully representative example, we show here a 400 by 400 image with a sinusoid superimposed on it. Such an example can possibly result in situations where periodic noise is added to an image, which might result from electrical or electromechanical interference during acquisition. So in this particular case, the observed image, if I call it y n1 and 2, equals the original image x n1 and 2 plus cosine 0.1 pi n2. So the sinusoid has frequency 0.1 pi. So such a sinusoidal signal is represented in the frequency domain by two deltas at plus minus 0.1 pi. So if one can estimate the frequency of this sinusoid, we can design a notch filter, as it's called, that will allow all frequencies in the image pass through the filter unchanged, except the frequencies where the sinusoid is located, which will be rejected. So it only rejects the minus 0.1 pi plus 0.1 pi frequency in the omega 2 dimension. So we do that and come back to the spatial domain, and the resulting image is this one. So we see that the little guy who was behind bars now has been freed.